All right, so good afternoon. So yesterday's lesson we talked about the rather simple graphs, so the most like fundamental ones like polar circles and lines. Today we're going to look at more complicated ones known as Limacons and Cardioids, as you can see from the name here. Do now is regarding this function here, r theta equals 1 minus 2 cosine theta, which is going to be an example of a Limacon. And for part A, I want you to just fill out this table evaluating this function at the following points. And then for part B, I want you to see what r of negative theta equals. And as a hint, right, there's a reminder that cosine negative theta is equal to cosine theta, right? It's an even function, if you remember from like our trig unit. Okay, so take a minute to do that, and then I'll go over it. Don't worry if you can't finish. I do want to move us along because there's quite a bit of material I want to cover today. So yeah, just take another 30 seconds on this. Okay, so let me go over the solution. So remember, the first part is just filling out this table, and then part B, we're going to evaluate r of negative theta. All right, so here's the table. Let me give you just a few examples. For example, like r of 0, it's going to be 1 minus 2 cosine 0. Cosine 0 is 1, so it'll be 1 minus 2, okay, which is negative 1. Then for 30 degrees, or pi over 6, we have 1 minus 2 cosine of pi over 6. Cosine pi over 6 is root 3 over 2. So we get 1 minus 2 times root 3 over 2, which is 1 minus root 3. In decimal form, that's negative 0.7, which is useful when we're plotting polar coordinates because we want to know like a decimal value so we can like know where to place it on the polar graph, right? So yeah, decimals are more useful in this case. But yeah, you would do the same thing for each of these angles. Again, don't worry if you didn't finish. And I don't want to really go through the calculation just because, yeah, it's something that we know how to do. But yeah, if you have any trouble with this, you can ask me now. But yeah, just for now, just copy this table. Okay. Yeah, from there, let's go to part B. We know that cosine negative theta equals cosine theta, right? Remember part B, we have to evaluate r of negative theta, see what happens. R of negative theta is going to be 1 minus 2 cosine negative theta. We know that cosine negative theta is equal to cosine theta, right? Because of this fact, this hint here that was on the slide. And therefore, r of negative theta is equal to r of theta, right? Because when we plug in negative theta, we get the same thing, right? So therefore, well, not therefore per se, but this is a fact that we'll explore today. This is symmetric about the polar axis. Okay, so if you remember from like xy, right? Like a parabola is symmetric about the y-axis. Let's see. I guess x cubed would be symmetric about the origin, right? So just examples of that. But here, polar graphs can also be symmetric about the polar axis, and then in a later lesson we'll look at two other symmetries. Okay, is anyone still copying this solution here? You can type in the chat or just speak up. All right, if not, then I'll move on to the slide. So this graph, r equals 1 minus 2 cosine theta, we're not going to graph it together. I'll just show you the decimals graph to save time. But yeah, that'll be on the next slide. All right, so this is what this graph looks like. If we plotted all those points and then connecting the dots. And also on the slide is the first test for symmetry, which was alluded to in the do now. Okay, so if r of negative theta equals r of theta, then the graph is symmetric about the polar axis. Okay, so the do now graph, r equals 1 minus 2 cosine theta, is symmetric about the polar axis, right? So what that means is, if you just draw a line along the polar axis, it'll divide the graph in half, right? If you flip it over the polar axis, then you get the same thing. Yeah, for the sake of your notes, I'll just write this down. Please write this test for symmetry and then also make a quick sketch of this graph here. Okay. Anyone still need the slide here? Okay, if not, I'll move on to the next slide, which talks about Limacons and cardioids, which is the type of graph we'll look at today. And the do now graph, this graph that you see right here, is a Limacon, okay, which is an old French word for snail. Okay. All right, Limacons. Can someone read this slide here? Oh yeah, Afron?
Limacons. Limacons have equations of the form r equals a plus minus b sine theta, or r equals a plus minus b cosine theta, where a is greater than 0 and b is greater than 0. If a is less than b, we have a limacon with an inner loop. If a equals b, we have a cardioid. Limacon is the old French word for snail.
All right, thank you for that. So yeah, the graph that we just saw from the do now, it's a Limacon with an inner loop, right? Because a is less than b, right? That function was 1 minus 2 cosine theta, right? So 1 is less than 2, which is, yeah, so we get this Limacon with inner loop. If a equals b, which we'll see in the next example, we'll get a cardioid. Okay. Can anyone guess what this graph will look like based on the name?
Cardioid graph. Perhaps.
Say it one more time.
Cardioid graph.
What shape does it look like, though, do you think? Like, like a limacon is like a snail. What would a cardioid look like?
Good question.
Yeah, that's okay. Well, from the chat, yeah, Mason, go ahead. Yeah.
A heart.
All right, yeah. Why do you say it looks like a heart?
Because like cardio is for the heart and stuff, so cardioid, heart.
Yeah, perfect. Yeah, that's all it is. It's a cardioid. So cardi being the prefix for things relating to the heart, right? Not the rapper Cardi B. Cardiology, cardiovascular. Yeah, having to do with the heart. So it's going to look like a heart. Yeah. Good inference skills, Jocelyn and Maysoon, Rafael. Okay. Anyone still need to copy this?
Yes, sorry.
Okay.
Thank you. Okay, I'm done. Thank you.
Anyone else still need it? Okay, gonna move on then. So next example is going to be a cardioid, as I said. So for that A will equal B, right, in this equation. Right. Okay. But here's the example. It's going to be 2 minus 2 sine theta. But to do so, I'm going to use this method that's cited in the textbook, right, the old textbook that we normally use in class. Can someone read this method here? Oh, yeah, go ahead, Johnson.
Rectangular graphs of polar equations. It can be helpful to graph the polar equation in rectangular coordinates. We can use the graph as a table of values instead of making a table manually.
All right, thank you for that. So yeah, as you'll see, we're going to graph the polar equation like a normal sine graph in this case, right? So it'll look like a graph that we saw, back in October, right? Typical sine graph. You do the same thing for like the cosine graph and they do now. But yeah, the point of this is to, instead of having to like make a table, like as it says here, making a table manually, as we did in the do now, instead of doing that, because that takes a long time, we can just draw the graph, and then from that we can extract information that'll tell us how to draw the graph. It's going to seem a little confusing at first because it's kind of like a new method, but I'll try my best to explain it. Yeah, just do bear with me. I'll also show you how to graph it using Desmos, which is like the most accurate way, right? Just use a graph calculator. Yeah, but yeah, feel free to use a graph calculator for your homework to check. But yeah, I'll show you what I did for the homework assignment. Okay, anyone still need to copy this? No? Okay. I'm going to move on then to the example. Okay, so as the textbook said, right, we're going to draw this graph as a regular sine graph. So what we're going to do is, think back to like October where we drew these graphs using a table. Okay, so we have 0 to 2 pi. Plug in 0, we get 2 minus 2 sine 0. So sine 0 is 0, right? So we just get 2. As another example, we do 3 pi over 2. We get 2 minus 2 sine 3 pi over 2. Sine 3 pi over 2 is -1, right? So we get 2 minus 2 times -1, which is 4. Right, but yeah, I don't want to emphasize this table because it's stuff we've seen before. But yeah, just copy down this table. And from this table, we would get this graph, right? So we have 0 over 2, which is here, pi over 2, 0, pi 2, which is here, 3 pi over 2, 4, and then 2 pi 2, which is here. Right, and then you get your sine graph. All right, anyone still copying down this first part?
I am.
Okay, yeah. Just let me know when you're done.
Oh, all right, I'm done.
Anyone still need it? Okay, I'm gonna move on to part B then. Okay, so as we're gonna use this method, right? So we're gonna use this information from this graph to draw a polar graph. And the way we're gonna do that is we're first gonna plot the points that we got from this table in polar coordinate form, and then we're gonna use the graph itself to analyze how the radius changes as the angle changes. Okay, so let's first start with the first half, which is polar coordinates, right? So the points from this table are 0, 2, right? Pi over 2, 0, pi over 2, etc., right? But in polar coordinate form, right, we have to switch the order, right? Because remember, r, which is the dependent variable, comes first, as we saw from the definition yesterday, right? R theta, right? So basically, these y values represent the r values, right? So we just switch the order of this. Okay, so instead of 0, 2, we get 2, 0. And then for pi over 2, 0, we get 0 pi over 2. For pi comma 2, we get 2 comma pi, right? Just switch the order, right? And then we will plot these coordinates. Okay, so let me start off by plotting these 5. Okay, so for example, like 2, 0 is located right here. 0 pi over 2, radius of 0, that's always going to give you an origin point or a pole point. And then we have 2 comma pi, 2, and then rotate 180. All right, we end up right there. That's going to be followed by 4, 3 pi over 2. So radius of 4 is like out here. And then we rotate 270 degrees, which is going to bring us right here. Lastly, 2 comma 2 pi, that's actually the same point as right here, right? So 2, rotate 360 degrees. Okay, so here is the more confusing part from this method. So just 4 sentences that they state in the textbook. So from 0 to pi over 2, from 0 to 90 degrees, which is this sector right here, right? This first quadrant. The radius is decreasing from an r of 2 to an r of 0, right? And we got that information from this graph here, right? So let me scroll up. Right, so from 0 to pi over 2, from 0 to 90 degrees, the radius is decreasing from 2 to 0. Okay, now how do we translate that to a polar graph? The way I'm going to do that is just identify like an example point, right? So between 0 and 90 degrees, let's say the angle is 30 degrees, right? An angle between 0 and 90. Let's choose 30 degrees. The radius is decreasing from an r value of 2 to an r value of 0. So basically, the r value has to be between 2 and 0. Let's choose the value of 1, right, just as an estimate. And I know this is kind of cheating because I have the graph right here, so that's actually is a point right there. But yeah, that's what I would do if we were in class and we were just plotting this without knowing the final shape. But yeah, just choose an example point that fits this description right here. Okay. So again, this point here is 1 comma 30 degrees, or 1 comma pi over 6. And then basically what you would do is, since you have these 3 points now, just draw a loop that connects all 3 points. And you get this first sector. Okay. So yeah, I'll just like connect these dots. You get that. Okay. Let me do one more example. From pi over 2 to pi, so 90 degrees to 180 degrees, the radius is increasing from 0 to 2. And again, that's still from this graph here. So from 0, it increases to 2 as the angle increases from 90 to 180. Okay, so as another example, let's use the angle 150 degrees. 150 degrees, that's located right here, right? So again, each of these lines is 15 degrees. So 180 minus 30 degrees, that locates us right here. And then the radius, I would estimate it to be 1, right? That's an easy, and which actually does match up. And then we have a point there. So yeah, you would just connect these 3 points here to create your second portion of the graph. Okay, but yeah, you would do the same thing for these next 2 sections, and then you would get, you know, this cardioid. But again, this is not a method I'm emphasizing. So I'm not requiring you to like do this on the homework, but you know, just be aware of, you know, the thinking behind it. So I do expect you to, you know, be able to draw this graph here. This is something that we've been doing. And then, you know, translate the points to polar coordinates, which is easy, just switch the order. And then just know what they're saying here, right? Like, yeah, from 0 to 9 degrees, radius is decreasing. So be able to interpret this graph here. But Yeah, this is just a method that, they cited in the textbook. I did want to mention it since it could come in handy sometimes. But yeah, it is more difficult just because we don't have polar graph paper, or at least I don't. I don't have a printer at home, unfortunately. So yeah, but yeah, I did want you to be aware of this procedure. Okay, I'm also going to show you Desmos really quickly. So yeah, feel free to use Desmos, the online graph calculator, to check your work on the homework. Yeah, does anyone still need to copy any of this? No? Okay. All right. But again, this is a cardioid, which kind of looks like a heart. Okay. All right. Let me get to the Desmos graph. Where was it? Okay, I think I closed it. One sec. All right, here it is. Okay, so this is desmos.com. Yeah, so feel free to use this to check your work. And I guess you could also use it for the next quiz if you want. I can't stop you there. But yeah, all you're gonna do is type in your function. So like you do r equals. So let's do the function that we just did, right? 2 minus 2 sine, and then for theta you just type in the letter theta. So that's spelled theta, right? And you get this function right here. They also allow you to toggle the domain. So like this is 0 to 360 degrees, right? Which is the graph that we just saw. You could change that to pi, for example, which is, the first 2 sections. You could change it to 3 pi over 2, which is the, 3 out of 4 sections. And then you can even do like, I don't know, like pi over 2 to pi if you want, right? But yeah, in total, the graph looks like that. Okay, that's the cardioid. And let me show you how I translated that to the homework. So again, this is desmos.com. Feel free to use it. For the first question on this homework assignment, I made a table as we did in the do now. Plotted 5 points. I used this symmetry fact, right? It's symmetric about the polar axis. So I plot these 5 points, and then I reflect over the polar axis. And then after that, I use Desmos to check if this is correct, right? Which it is. Okay. But yeah, this is what I did for the homework. Just table and okay. All right. Yeah. A couple closing announcements. One, there's SGI as always at 2:47. Next is our next quiz is going to be the Friday after we come back from break. So whatever Friday that is after New Year's. So that'll be quiz 5. Okay. Lastly, so there's no mid-year exam this year, but as we normally do in pre-calc. But instead of that, I'm going to have a group project, most likely, and that will replace your lowest grade. And I'll assign that like probably, I might send it out over winter break over Google Classroom, and then you'll have like until the end of the semester, which is end of January, to complete it. Okay. But yeah, if there are no further questions, I will leave you here and have a great rest of the day. I'll see you all tomorrow.
Have a good day.
Thank you very much. Have a great day.
Thank you too.